Hello, dear students. In the last class, we were studying the progression of errors in physical equations, or say progression of errors in algebraic operations when we do on physical quantities. And we saw the maximum error present when we add two physical quantities is always equal to the sum of the errors present in each physical quantity. Let me say like this: if we had the error in the first measurement as x plus or minus delta x, and the second is y plus or minus delta y, and when I added the two x plus or minus z plus or minus delta z is equal to, when I found the sum of these two, we found the maximum error to be present here is equal to delta x plus delta y. This was the first thing we saw. Second, we saw when we subtracted the two, we found on subtraction the maximum error present in the difference was equal to x plus or minus delta x minus y plus or minus delta y. The maximum error present, again here it was z is equal to delta x plus delta y. Today we are going to find what will be the maximum error present when I try to find the product of two physical quantities. Say this time, say for me, the first physical quantity that has the true value, I am going to say x, and the next physical quantity it will have is y. And when I find the product of the two true values, then I am going to get z is equal to x times y. This is the true product, and x and y are the true measure. However, when we do measurement and find or observe the physical quantity, the value that we observe, the first quantity, we will have some error. So, therefore, I am going to present this way. This is the first quantity, and the second physical quantity that I have is x plus or minus delta y. And when I find the product of the two, say like this, x plus or minus delta x times y plus or minus delta y, I am going to get the product in turn. The product is going to have the error z plus or minus delta z. In that case, when I try to find the product, then x times y, so this is xy, then x into delta y, I am going to have plus or minus x times delta y, then this will have plus or minus y times delta x, and when I do find the product here, I am going to have delta x times delta y. Already we know delta x is a small amount present in terms of error. So, delta y is also very small in amount. When we try to find very small amount of two quantities product, then this is going to be very small. This is going to be very small, and and this product can be neglected from calculation. So, when we neglect the calculation, in my calculation the value that I am going to obtain in the form of product will not matter much, and therefore, I have z plus or minus delta z is equal to x times y plus or minus, say y terms delta x plus or minus x terms delta y. I am going to divide both sides by z. So, say this side I am multiplying or dividing by z, and here z is equal to x times y. So, either I divide by z or x y, both mean same for me. So, in that case I will have 1 plus or minus delta z over z is equal to x into y over x into y plus or minus this I am going to get say delta x over x, because y and y will cancel one another, x and x will cancel one another, I will be left with delta y. Otherwise this and this goes off, I am left with delta z by z is equal to plus or minus delta x by x or plus or minus delta y. When I see the 4 options available, all those 4 options will be like this: delta z by z. I am going to have the first option delta x by x plus delta y by y. The second option I am going to have minus delta x over x plus delta y over y. Third option I am going to have delta x over x minus delta y over y. The fourth option I am going to have delta x over x and minus delta y over y. Now, delta x by x is called fractional error, already we have seen. So, this is the fractional error of the measurement of the physical quantity. Delta y by y is the fractional error of measurement of this physical quantity. So, therefore, these are the sum of the fractional errors of the 2 quantities that we are trying to find the product. Now, what I actually want to calculate? I actually want to calculate that what is the maximum possible error that will present when I am trying to find the product of the 2 measurements. And I see the maximum possible error, in the sense the maximum possible fractional error is going to be the third one. Say the maximum possible fractional error will be equal to delta x over x plus delta y over y, which is the final fractional error that will be present. If I am asked what is the maximum error present in the product, then that is going to be delta z will be equal to delta x over x plus delta y over y times z. If I multiply, then this will be the maximum error in the product. Next, the maximum error present in quotient. So, thus let us try to find the maximum error, or say I want to find what is the fractional error. So, maximum fractional error in quotient. So, let me say that I have a true physical quantity x and true physical quantity y. When I try to find, then z is the quotient of x by y. So, if I try to measure, on measuring this physical quantity, I am going to have some very small error. Similarly, when we observe y, then the measurement is going to have some error. So, when I try to find the quotient of the 2 like this, x plus or minus delta x over y plus or minus delta y, then the quotient is going to have the error like this, or I am going to get the final quotient like this, and this quotient will have some error. I want to find what is the maximum possible error in the quotient, that too fractional error I want to find. In that case, I can rewrite this expression as z plus or minus delta z is equal to, I can say x I take common. So, I will have 1 plus or minus delta x over x, and here I want to take y outside. I am going to have 1 plus or minus delta y over y. Else I can write like this: 1 plus or minus delta x over x times 1 plus or minus delta y over y power minus 1. And I take z common here. So, I am left with 1 plus or minus delta z. From the true measure, I know that z is equal to x over y. So, z of x y is cancelled out, and As such, I am left with 1 plus or minus here it is delta z over z. So, therefore, delta z over z is equal to 1 plus or minus delta x over x times, when I see this, I told you that the delta x is very small quantity and y comparatively is very much larger in comparison to the amount of error present in a measurement. So, therefore, the numerator is very small, the denominator is very large. So, therefore, this quantity is going to be very small. So, thus when this second term is very small, so I can use the binomial theorem to expand this one. On expansion, the higher order powers will have very negligible amount of value. So, we will neglect those higher order powers and therefore, we are going to retain the power 1. So, therefore, I will have 1 in place of plus, this will turn this plus into minus and minus into plus. So, therefore, I have minus plus delta y over y. So, this is the term on expanding in terms of binomial theorem. In that case, when I try to find the product, I am going to have 1 minus plus 1 times 1 delta y over y, say minus plus, and if I multiply this plus or minus delta x over x minus plus delta x times delta y times y. In the previous case, as we saw, these quantities are very small. So, therefore, they are very small and can be neglected, very small and can be neglected. In that case, we have 1 plus or minus delta z over z is equal to 1 minus plus delta y over y plus or minus delta x over x. This and this goes off, else I am left with delta z or z. I am writing this one in a particular order which will be convenient for me, and therefore, I have this. Now, in the end result, I see I have 4 possible values here. So, now I want to write all the 4 possible values separately. So, the first value I am going to write delta x minus delta y. The second one will be minus delta x over x and minus delta y over y, minus delta x over x plus delta y over y plus delta x over x and plus delta y over y. I know delta x by x is a fractional value, delta y by y is also a fractional value. So, therefore, this is the difference of 2 fractional values. Again 2 negative fractional errors, 1 negative and 1 positive. These are the 2 positive fractional errors. Now, if I ask you which one is the maximum fractional error present while trying to find the quotient, I say this is the maximum possible fractional error. So, therefore, the maximum fractional error that will be present in the quotient will be sum of the fractional errors of the 2 physical quantities x and y. So, this is the maximum fractional error that is going to be present while trying to find the quotient of 2 observed physical quantities. As such, if I am asked to calculate the maximum possible error present in the quotient, then I am going to write the sum of 2 fractional error times this z I am going to multiply here. So, this will be the maximum possible error present in the quotient. Let us have another concept. If anything or any physical quantity is raised to some power and I want to calculate on raising to some power what will be the maximum error present in it. So, therefore, the maximum error in raising or when maximum error when a physical quantity is raised to power n. Let us try to see. Let me say that the true observed or the true physical quantity is x and it is raised to power n, and on raising the true physical quantity to power n, I am getting the answer as z. So, this is the true product. However, when I try to measure the physical quantity x, I am going to have the value x plus or minus delta x power n, and on raising this observed physical quantity to power n, I am going to have z plus or minus delta z. In the sense, when I observe the physical quantity, I have some error, and if I try to find the power n to this measured physical quantity, in the result I am going to have this much error, and I want to calculate what will be the maximum error present in it. In that case, I am going to take z outside. So, I will have 1 plus or minus delta z is equal to, when I try to pull out this x from here, I know that I have power n also. So, when I will be pulling out x, so x will come out in this form, x power n. So, 1 plus or minus delta x over x to the power n. Now, I know that the true measure x z is equal to x power n. So, this is gone. So, I am left with 1 plus or minus, this is delta z over z is equal to, now already we know here I have x. We already know that delta x at the numerator is very small and at the denominator x is a very large quantity comparatively. So, therefore, this quotient itself is very small. So, I can use binomial theorem to expand this this expression. At the same time, the higher order powers can be neglected. So, therefore, I have 1 plus or minus this n times delta x by x. Now, I know that this 1 and 1 can be written off. As such, I am left with delta z over z is equal to, I will be having plus or minus n times delta x over x. Maximum error I want to find. This time I have fractional error. So, what could be the maximum fractional error if you ask? Then the maximum fractional error is going to be positive quantity. So, I will be having n delta x over x. If I am asked what is the maximum error is delta z. So, I can write this delta z as delta z is equal to n times delta x over x into z. So, if I do this way, then I will get what is the maximum possible error present in a physical quantity that is raised to power n. Dear students, let us apply the concept of progression of errors in doing algebraic operations to a problem. Here I am given with a problem. It says that if z is equal to x power a y power b over w power c, it says that x is a true physical quantity, y is a true physical quantity, and w is also a true physical quantity. When I do this algebraic operation, I am going to get the true answer as z, and I am asked to calculate what is the maximum fractional error when I do this calculation. Also, I need to calculate what is the maximum percentage error. So, let us try to do this first. In that case, when I look at my problem, so I have z is equal to x power a, y power b and w power c. When I see x and y, they are in product. The result of this product and wc are in quotient form. So, the maximum possible error or the maximum possible fractional error just we saw, this will be equal to, now you see x is raised to power a. In that case, power times the error or fractional error delta x over x. This will be the error for x power a. Y power b What will be the maximum fractional error? This is going to be b delta y over y, but they are in product and therefore their total fractional error is going to be the sum of the two errors. Since WC is in the denominator, again for finding the maximum fractional error, I am going to have the fractional error of W power C and I am going to have as a sum with these quantities, and therefore this will be plus C times. So, this is the maximum fractional error that will be present in my equation. When I solve this equation, the maximum fractional error, first one. Then I am asked to calculate what is the maximum percentage error. We have already studied the concept that when you calculate the fractional error, if you multiply this fractional error with 100, then you will express it in terms of percentage error. Otherwise, delta z by z is equal to and if I multiply this into 100, then whatever the value get, I am going to write in terms of percent. So, therefore, this will be the percentage error, maximum percentage error that will be present when I do this calculation. Let us move on to another concept. The concept is about significant figure. Often you will get questions in the examination, even in the competitive examination also. So, we need to understand the concept. What do we actually mean by a significant figure? I told you that we use measuring instrument to measure physical quantities. When we measure physical quantity, I said the measured value or observed value always has some amount of error. Now, question may be asked, why is this error? Say, for example, you are given a length of this much and you are asked to measure the measurement, and you keep your scale here and say your 0 lies exactly here at the starting point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So, let me say this is point A, this is point B. A and B are the end points of the straight line. I am using the centimeter scale and I see that the point A exactly coincides with 0 and the point B exactly lies between 1.4 and 1.5, 1.4 and 1.5 centimeter. So, this is what the length is, but how would I express? Either I will be expressing it as 1.4 centimeter, otherwise I would say that 1.5 centimeter. Be mindful, when I say 1.4 centimeter, that means the line is slightly bigger than 1.4 centimeter. If I say 1.5 centimeter, then my line is slightly smaller than 1.5 centimeter. So, when I write 1.4 or 1.5, both the measurements are not correct. In that case, some students would say that, sir, the point B is lying in between 4 and 5. So, you write 1.45 centimeter. This is totally wrong because the instrument that you use to measure is capable of measuring the smallest quantity, that is equal to 0.1 centimeter. So, 0.1 centimeter, the smallest measurement that you can make in a measuring instrument is called as least count. So, when you have a device which has a least count, then the measured value cannot have a value smaller than least count. So, therefore, we cannot express the measurement in terms of 1.45 centimeter because the least count of my scale is 0.1 centimeter. So, thus what we actually mean is, exactly if I look at, see, the 1 centimeter I told, this value is truly correct. So, if I see one digit is exactly right, but I have doubt in this digit. So, the last single digit always we are going to have doubts. So, this digit is not certain. So, here the definition says that whenever we measure any quantity, the digits which are absolutely correct, for me the absolutely correct digit is 1 now. So, the absolutely correct digit plus the first uncertain digit, the first uncertain digit is 4. I cannot write 5. If I write 5, that will not be taken into account because I will be expressing my answer in terms of the least count only. So, therefore, in a measured value, absolutely correct digits plus the first uncertain digit taken together, we call it as significant figure. Hope you understood. Now, in that case, we have certain rules to count the significant figures. In any measurement, if we have, the rule 1 says all the non-zero digits are significant. For example, let me say 345 plus 27 centimeter if I say. All the digits are non-zero. So, therefore, they are significant. So, if I am asked what is the significant figure in this measurement, I would say 1, 2, 3, 4, 5. So, 5 significant figures are there. Now, by looking at this, I also come to know that the least count is 0.01 centimeter, right. Then the second rule says that the zeros between two non-zero digits are significant. What it says, let me suppose that 20043 say millimeter. So, this is my measurement. When I do this measurement, then I have zeros, but these zeros are lying in between two non-zero digits. So, when you have zeros between two non-zero digits, they are also significant. So, in this case 2, I have 5 significant number, 5 significant numbers or figures. Third rule says that trailing zeros after decimal point are significant. What do we mean by this? Let me suppose that 2.3000 centimeter I say. So, after decimal point, these are trailing zeros, the zeros that comes as a tail. So, it is a trailing zeros. In that case, these trailing zeros are also significant. So, in my case, I will have 1, 2, 3, 4, 5 significant figures, 5 significant figures in this case. The next rule says that powers of 10 are never taken into account as significant figure. What do we mean by it? Let me suppose that I have 3.2 into 10 power 7 meter or say meter per second. In that case, the power of 10, this will not contribute anything towards counting significant figure. So, if I am asked what is the number of significant figures, so this is 2, 2 is the significant figure. Then if I go to the fifth rule, what it says, if a measured value is less than 1, in the sense lay point 0.0043200 like this, okay, and say some millimeter. So, it says if the measured value is less than 1, so if I am asked whether it is less than 1, of course it is less than 1. Then all the zeros occurring left of first non-zero digit are not significant. That means after decimal point, the zeros up to the first non-zero digit, these are not significant. In that case, if I am asked what is the significant figure of this measurement, then I would say that I know the rule, after decimal point the trailing zeros are significant figures. So, in that case these zeros are significant. So, therefore, I will have 1, 2, 3, 4, 5 again coincidentally my examples have 5 significant figures in every case. It is a coincident. Okay. Then the rule says changing measurement from one system of unit to another system leaves the significant figures unchanged. What do I mean by it? Let me say I have 23 meter So, I have two significant figure, and if I am asked to convert this one into centimeter, I know that I am going to write 2300 centimeter. So, in this case it is significant figure 2, here also the significant figure is 2, but it is always confusing. Therefore, in physics we follow a rule that instead of writing like this, we will write in this form 23 into 10 power 2 centimeter. So, now we know the rule that anything or power raised to 10 will not be taken into count when we calculate the significant figure. So, in that case here too I have two significant figure, here also I have two significant figures. Then comes trailing or terminal zeros in a number without decimal point. Here the example, again I can repeat, 23 meter, if I convert this one into centimeter like this, if I convert this one into millimeter, then this will be like this. Now, I see that this measurement has no decimal point. So, this rule says that when there is no decimal point, the trailing zeros are not significant. In that case, the significant figure, here it is 2 and here it is 2, here it is 2. The most beautiful rule, it says that exact measurement, that means the true measured value of any physical quantity will always have infinite number of significant figures. Of course, when you try to measure the device, use the device to measure a physical quantity, then if it has got least count, then there is a limitation to approach towards the true value. So, that as such, if I have a measuring instrument which has no least significant figure, say, so therefore, that measured value will have infinite significant figures. So, dear students, with this we come to the end of the chapter. In the next class, we shall come up with the new chapter in class 11 physics. Thank you very much. Keep enjoying.